Hi everyone. In this video we're going to talk about section 2.5, which is the last section of chapter 2. And section 2.5 is about independence. And so conditional probability gives us the opportunity to revise our assignment of probability to an event when we are subsequently informed about another event occurring. So, you have some idea of what probability about a single event is, and then if you're informed about another piece of information, that may change your mind. So given B, your probability about A may be different. Okay. Usually, that subsequent knowledge changes your probability assigned to the first event. But there are some cases in which it doesn't. Okay? And in those cases, the two events that you're looking at, which we'll usually call A and B, they're considered to be independent events. So, as an example, if I say the probability that it's going to snow today is 40%. Okay, so A is that it's going to snow today. But I tell you, wait, I'm going to tell you something else first, or after it. Subsequently, I ate cereal for breakfast today. Now, what's the probability that's going to snow? The logical answer is probably 40%. Okay, because what I ate for breakfast and whether or not it's going to snow today are they don't have anything to do with each other, right? They can both happen. I can eat cereal for breakfast, and it can snow today, but one does not affect the other. Okay, the fact that I ate cereal does not change your idea about how likely it is it's going to snow today. Probably, unless I eat cereal only on days when it snows. Okay, but we don't know that, so those are technically independent. Okay, independent. So the formal definition is this. For two events A and B, they are independent if the probability of A given B is equal to the probability of A. So it's as if the conditioning weren't even there. If those two are equal, then they're independent. Okay. If they're not independent, they are dependent. So if they aren't equal, then they're dependent. And important to note, in which I sort of touched on previously, but not sort of overtly, is that mutually exclusive and independent are not the same. This is something that is sort of a tripping point or a stumbling point for a lot of students. Mutually exclusive events means that two events cannot happen at the same time. Okay? There's nothing in common. Independent events means that one does not have any effect on the other. They sound similar, but in fact they're not. Okay? Furthermore, they cannot be more different than each other. So mutually exclusive events or disjoint really actually implies a very strong level of dependence. Okay, so if you think about it for a second, if I know that A and B are mutually exclusive, that means that they cannot happen at the same time. They can't happen together. And so that means that if I know that one happens, so if I know that A happened, then I know for certain that B cannot happen because they're mutually exclusive. And so, in fact, they're highly dependent on each other. If one happens, then the other can't. Okay, so it's the exact opposite, almost, of independence. So if one event occurs and the other can't, that's mutually exclusive. Independent means that A doesn't have any effect on B, or B doesn't have any effect on A. Okay, so they are very different. So don't get them confused. So, furthermore, the definition of independence gives us an important proposition, which comes from the general multiplication rule that we saw before. Okay, and so this proposition is A and B are independent if and only if something happens. Okay, and I'm going to use if and only if throughout this course, and I will shorten that to IFF. Okay, and so IFF means if and only if in mathematical notation, and the thing that needs to happen is that the probability of the intersection is equal to the multiplication of the probabilities, okay, or the product of the individual events, probabilities of individual events. Okay. Now, the general multiplication rule says this. Okay, in previous videos, I had it incorrectly, and I fixed it here. It says that the probability of A and B is equal to the probability of A given B times the probability of B. That's the general multiplication rule that comes as a consequence of just the definition of conditional probability. But A and B being independent means that probability of A given B here is equal to the probability of A if A and B are independent. Yes? And so let me get rid of that, and then up goes the probability of A, and we get this. Okay? And so this gives us a way to test if something is independent or not. Okay? If the probability of the intersection is equal to the product of the individual probabilities of the individual events. Okay? So, an example, once I get rid of all my writing. It's known that 30% of a company's washing machines require service while under warranty, whereas only 10% of its dryers that it sells need such service. Okay? If someone purchases, I'm sorry, I don't know why the B is capitalized here. If someone purchases both a washer and dryer from the company, what's the probability that both machines will need warranty service? Okay, so if we let A, I'm sorry, time that it quits out on me. So if we let A be that we sell a washer, and B is the dryer. Okay. I guess we should be more. We should be more concrete about what A and B are. Really, A is that we need to service the washer while under warranty. So we'll say washer service under warranty, and B is dryer service under warranty. Okay, so A is washer service, B is dryer service. Again, apologies for bad handwriting. We're looking for the probability of the intersection, the probability that A and B happen, that we have to service, they buy and have to service both. Okay, and you have to think, is servicing a washer and servicing a dryer, are they independent or not? Well, the washer going bad probably has nothing to do with the dryer going bad. They can both happen, okay, and certainly they happen to people all the time, and the people think they have terrible luck that both the washer and the dryer malfunction, okay, under warranty, which is great. After warranty, not so great. They can both happen at the same time, so they're like not mutually exclusive, and in fact, probably one does not affect the other. Okay, unless there's some outside circumstances, like they're both hooked up to faulty wiring, like electrical surges, so on and so forth. But we aren't really thinking about that too much. And so we know that, or we can assume that A and B are independent. Okay, I think it's a safe assumption to assume that they are independent, that one does not have any effect on the other. And so with that happening, we can say that the probability of the intersection is equal to the product of the individual probabilities. And so we know those 30% of a washing machines require service under warranty. So it's the probability that A happens is 0.3 and the probability that B happens is 0.1. Okay, and so to get this intersection, we can say it's 0.3 times 0.1. And when you do that multiplication, you get 0.03. And so this means that the probability of getting both and having both have to be serviced before the warranty runs out is 3%. Okay? So that's how we can use that sort of definition of independence there. And so for the your turn on this video and for the end of Chapter 2, end of Section 2.5, I want you to consider an experiment of sequentially rolling two fair six-sided die. Okay, and I'm sorry, I have sequentially in there 2 times, so take one of them out. Next, consider the following events. Okay, so A is the face of the first die is a 1. B is the face of the second die is a 3. Okay, C, the sum of the two faces is 9. And D is the sum of the two faces is 7. I want you to determine whether the following pairs of events are independent or not. Okay, and so there's 3 here, B and C, A and C, and then A and D. Okay, and so what you need to do for this your turn is you need to check if that condition is met. Okay, so you need to check if the probability that A and B is equal to the probability of A times the probability of B. And always remember that in here in A and B, which is confusing because I also have A and B over here, that I mean general events A and B. Okay, not these specific A and B. So for number 1, it's actually B and C. For number 2, it's A and C. Number 3, it's A and D. Okay, so make sure that they are, you don't confuse the actual with the general. Okay, so I want you to check when I say to make sure if they're independent or not. I need you to check if this side is equal to this side. Okay, so there have to be some you have to think through these problems, think through rolling the dice. I'll give you some hints down here. I want you to actually write out the sample space. There are 36 outcomes. Each one is equally likely because they're fair die. Okay, and then I give you some direction in that third hint. Okay, so think about something like for the probability of the intersection, B and C, the face of the first die is a 3 and the sum of the two faces is a 9. How many ways can that happen? Okay, find out how many ways that can happen and divide it by 36. That's the probability of the intersection. Then for each individual part, B and C, go through there. How many ways can I roll 2 die and the face of that first die is a 3? Do that. Sum of 2 dice is 9. Do that. Then multiply those probabilities together, see if they equal the probability of the intersection. Okay, and then do that for all 3. All right, so that's the end of Chapter 2. That's the end of Section 2.5 and the end of this video.